What if the way we've been teaching machines language is fundamentally backwards? Humans don't need 10,000 labeled examples to learn a new task. You can tell someone, here are 2 examples of bravery, give me a third, and they just do it. Yet our best natural language processing systems, even the impressive ones built on pre-training and fine-tuning, still demand massive task-specific datasets for every new problem you throw at them. This paper from OpenAI asks a provocative question. What if we just made the model dramatically bigger and stopped fine-tuning altogether? To set the stage, let me explain where the field was. The dominant recipe involved taking a large transformer language model, pre-training it on huge amounts of text using self-supervised learning where it predicts the next token, and then fine-tuning it on a labeled dataset for whatever specific task you cared about, like sentiment classification or question answering. Models like BERT and its descendants pushed this approach to remarkable heights. But there are 3 problems with this paradigm. First, you need a fresh labeled dataset for every new task, which is expensive and often impossible. Second, when you fine-tune a giant model on a narrow dataset, it tends to overfit to quirks of that dataset rather than truly generalizing. Third, it just doesn't match how humans actually learn language, which suggests we might be missing something important. The alternative the authors pursue is called in-context learning, and it's worth understanding the intuition here. Think of it like this. During pre-training on a vast corpus, the model encounters countless implicit subtasks embedded in text, things like translating, summarizing, answering questions, completing patterns. The hypothesis is that as the model gets large enough, it doesn't just memorize facts, it actually develops a kind of meta-skill where it can recognize what task is being asked of it from a few examples in its input, and then perform that task by simply predicting what comes next. No weight updates, no gradient descent at inference time, just pattern recognition happening inside a single forward pass through the network. So they built GPT-3, which stands for Generative Pre-trained Transformer version 3. It's an autoregressive language model with 175 billion parameters, roughly 10 times larger than any prior dense model. The architecture is essentially the same as GPT-2, a stack of transformer decoder layers with some alternating dense and locally banded sparse attention patterns borrowed from the sparse transformer work. The context window holds 48 tokens. They trained 8 different model sizes ranging from 125 million up to 175 billion parameters specifically, so they could chart how performance scales with size. The training data is a carefully curated mix. They started with Common Crawl, which is essentially a scrape of much of the public web, but raw Common Crawl is full of garbage. So they filtered it by training a classifier to identify content similar to known high-quality sources, then did fuzzy deduplication to remove near-duplicate documents, and finally mixed in higher-quality sources like an expanded web text, 2 books corpora, and English Wikipedia. Importantly, they don't sample these datasets proportionally to size. They oversample the higher-quality sources, so Wikipedia gets seen about 3 times during training while filtered. Common Crawl gets seen less than half a time. The total training corpus is around 300 billion tokens. Now here's the crucial experimental setup. They evaluate the model in 3 settings without ever updating its weights. 0 shot means you just give the model a natural language description of the task, like translate English to French, followed by an English sentence, and see what it produces. 1 shot means you give the description plus a single worked example before the actual query. Few shot means you stuff as many examples as fit in the context window, typically between 10 and 100. Crucially, these are all evaluated by simply feeding text into the model and reading what comes out. There is no training happening, no parameters changing. It's pure inference. The results are striking in several ways. On the Lambda benchmark, which tests long-range dependency by asking the model to predict the last word of a paragraph. GPT-3 in the few-shot setting hits 86.4% accuracy, an 18-point improvement over the prior state of the art. On Trivia QA in the closed book setting, meaning no retrieval allowed, GPT-3 few-shot reaches 71.2%, beating fine-tuned models. On translation into English, few-shot GPT-3 outperforms prior unsupervised neural machine translation work by about 5 BLEU points. And perhaps most surprisingly, GPT-3 can do 3-digit arithmetic with 80% accuracy, 2-digit multiplication at 29%, and even handle compound expressions like 9 times the quantity 7 plus 5. The authors checked carefully, and these arithmetic problems are not memorized from training data. The model is actually computing, but the picture isn't uniformly rosy. On natural language inference tasks like ANLI and on tasks requiring fine-grained comparison between two sentences like WIC, GPT-3 barely beats random chance. On reading comprehension datasets like race and quasi, it lags far behind fine-tuned approaches. The pattern that emerges is that tasks involving comparing or reasoning about the relationship between two pieces of text seem to be where in-context learning hits a wall. There's also a consistent finding that the gap between zero-shot and few-shot performance widens as models get larger, which is the central evidence for the meta-learning hypothesis. Bigger models aren't just better at tasks, they're better at learning tasks from context. The authors are also commendably upfront about limitations and risks. Data contamination is a real concern when you train on most of the internet because test sets for benchmarks are often online too. They built tools to measure overlap and flagged results where contamination might inflate scores. They also discuss broader societal impacts seriously, including the ability to generate news articles that humans struggle to distinguish from real ones, biases the model has absorbed from training data, and the enormous energy costs of training. And there are deeper limitations they acknowledge. The model still makes simple mistakes a human wouldn't. It has no grounded understanding of the physical world, and its sample efficiency during pre-training is vastly worse than human learning, requiring orders of magnitude more text than a person sees in a lifetime. Now let's walk through some questions you might have after hearing all of this. First, why does scale matter so much for in-context learning specifically? The intuition is that in-context learning requires the model to internally represent a vast number of possible tasks and the ability to recognize which one is being demonstrated. A small model might be able to do next token prediction reasonably well by learning surface statistics, but recognizing, oh, this is a translation task, or oh, this is an analogy task from a few examples requires something more like a learned library of task templates. Larger models have the capacity to build up that library during pre-training, and the empirical scaling curves show this ability emerging smoothly as you add parameters. Second, isn't this just memorization with extra steps? Why should we believe the model is actually learning at inference time rather than retrieving patterns it saw during training? This is a fair concern, and the authors address it partially. The arithmetic experiments are particularly telling because they searched training data for the specific problems and found essentially no matches, yet the model still solves them. The word unscrambling tasks are designed to be artificial and unlikely to appear in training. And the in-context learning curves, which show performance improving as you add more examples to the prompt within a single forward pass, are hard to explain through pure memorization. That said, the line between learning and sophisticated pattern matching from training is philosophically murky. Third, why not just fine-tune GPT-3 if you want the best performance? You absolutely could, and the authors note this as future work. But the whole point of the paper is to demonstrate that a single general model can be deployed across hundreds of tasks without per-task data collection and training infrastructure. In production, the operational simplicity of one model handling everything through prompting is enormously valuable, even if a fine-tuned model would beat it on any specific benchmark. The paper is establishing that this trade-off is now viable, not that it's always optimal. For large-scale recommendation systems, the implications here are concrete. The in-context learning paradigm suggests a path toward unified models that can handle many recommendation surfaces like home feed ranking, search ranking, related items, and notification ranking without training separate models for each. You could imagine encoding user behavior sequences and a small number of demonstration examples for the current task into a prompt, and having a single large foundation model produce the relevant score or candidate. This is essentially what generative retrieval and semantic ID approaches are now exploring at companies like YouTube and Pinterest. More practically, the scaling laws and the demonstration that smooth performance gains come from larger models trained on more diverse data have directly informed how recommendation teams think about scaling their own sequence models for user representation. The lesson that a single large model can absorb knowledge across many implicit subtasks during pre-training maps cleanly onto multitask and multi-domain recommendation, where you want one user embedding model that captures behavior signals useful across video, ads, commerce, and social surfaces, rather than fragmented per-vertical models that don't share statistical strength.